try to give some kind of background of the other deep learning models very quickly, and then go into the discussion on how these transformer models are different from the other deep learning models and the kind of tasks these transformer models can be used. Then we try to understand the underlying principles and concepts behind these transformer models. Then we'll try to look at what is called the structure of these transformer models and how these models can be used for solving several tasks in different domains. No, okay. I will not be taking any specific applications in the presentation, right? And but I'll tell you what kind of problems for which these transformer models can be typically used for, right? And there are many papers coming out nowadays on applications of these transformer models for a variety of tasks. So one can refer to those papers for how these transformer models are applied for those tasks in the different domains. I'm sure all of you have gone through a number of lectures related to the machine learning techniques and a few deep learning models in this workshop. I'll try to give my perspective and then try to link it up with the transformer models. I think all of you are familiar with what is called a typical classification task. Let's say if I take an image classification task where the classes are the defined. In this case, what I'm showing you here are the images of the animals. In each row of images, we have the images of a particular type of animal. So like this, we can collect a large number of examples for each of the classes, and then we build a classification model to perform the classification task. So after the model is built, if I give any image, the model should be able to tell me to which animal that test image belongs to. Okay, it's a fairly classical task, and there have been a number of approaches that have been developed in the past 60 years in the machine learning field. Okay, but typically what is done, one of the conventional techniques is you extract a feature vector from an image and then give it as input to any classification model like a Bayes classifier or a support vector machine or a neural network model. So a typical neural network model in the early days in 80s and 90s used to have a simple structure with the input layer, where the number of nodes in the input layer is D, that is the number of features that we have extracted from the example, in this case from an image. Then the number of nodes in the output layer will be equal to the number of classes. And there can be one or more hidden layers. And the number of hidden layers and the number of nodes in these hidden layers is chosen according to the complexity of the model. And as the complexity of the model increases, as the number of hidden layers and the number of nodes in the hidden layer increases, the number of the connections among the nodes will be increasing. Therefore, the number of parameters, weight parameters will be increasing. And the thumb rule, as all of you know, in the machine learning techniques, is that one requires at least 10 times the number of parameters as the labeled examples to train these kind of models, right? In the 80s and 90s, till this deep learning model field has come into the emergence, we used to have models with only one or two hidden layers. Nowadays, they are called as the shallow neural networks. And any model with any such structure with more than two hidden layers is typically called as a deep feed-forward neural network. So this can also be used for solving problems like static pattern classification tasks, where the static pattern refers to a feature vector extracted from an example and then given as input to the model. Then we train this model to perform the classification task. Okay, and there are several domains where this kind of deep feed-forward neural networks are used for the static pattern classification task, especially if the number of classes is large and if the complexity of the classification task is large. What do you mean by the complexity of the classification task? The classes are very similar to one another, so it's very difficult to discriminate among the classes. So that's where these highly complex models can be used. But if you want to build the models which are specific to the type of the data that you're dealing with, right, especially if you're talking about the image data, then it has been shown that the models like the convolutional neural networks, which are specifically designed for the image type data, which can deal with a lot of variations like the translation variations, scale variations, and so on in the images. And the model can be trained to be invariant to this kind of distortions. As you might have been already told in the earlier lectures in this workshop, right? Typically, there is what is called a feature map in a convolutional neural network, and a convolutional layer consists of several such feature maps, and each feature map is a set of neurons where a neuron in a feature map is connected to a part of the input image, which is called the receptive field. Then we perform a convolution operation and then generate an output from this neuron, which forms a new feature that's extracted from the receptive field. And typically, all the neurons in a particular feature map share the same weight, so that they extract the same feature from the different parts of the image. And that set of neurons which extract the particular type of feature from the different receptive fields in the given image is what is called a feature map. And typically, it's not enough if we extract only one feature from each receptive field. We want to extract multiple features from the same receptive field. So therefore, we use multiple features. So basically, we can construct this convolutional layer as a feature extraction process, right? And then we combine the features from these feature maps in the pooling layer by doing some kind of an average operation. Then we again go through the similar kind of an operation in the next convolutional layer to extract some other set of new features and so on, right? And a typical convolutional neural network like this, what has been shown here, which was the LeNet 5, was mainly designed for the handwritten character recognition. What is important to note here is that the number of connections in the model is very large, right? Let's say in this specific case, there are close to 278,000 connections, but there are many weights that are shared among the nodes in a particular feature map. Therefore, the actual number of parameters to be learned during the training process is much less compared to the total number of connections in the model. So this weight sharing becomes very critical when you are talking about the complex models, as we'll be seeing later. Even in the case of transformer models, we'll be making use of similar principles like weight share. So this convolutional neural network has been shown to be very effective for image type of data, and there are many advances related to this. And one such advanced deep convolutional neural network is what is called as the VGGNet, and it has been mainly designed to deal with a very challenging classification task of color images belonging to 1,000 classes to the ImageNet data. As you can see here, the structure of this model is very complex, right? All these white boxes that are shown here are the convolutional layers, and the blue boxes that are shown here are the pooling layers. And of course, there are what are called the fully connected layers. And finally, we have the softmax layer, which performs the classification task with 1,000 nodes, right? So typically, this is the kind of a structure of deep CNN that is required to perform a very complex classification task for our 1,000 classes, where many classes are very similar to one another. And these deep CNNs have been shown to be very successful in performing this classification task. And there have been many other deep learning, deep CNN models like ResNet, GoogleNet, and so on, right? And you can find the details of several of these models in a very comprehensive paper that was published in 2017, right? That will tell you what are the different types of deep CNNs and how they help us to perform this classification task in the ImageNet data in a very efficient manner. Okay. So basically, what this deep CNN does is take the image itself as input, right, and then extracts the features from the image as part of the training process, right, and then solves the classification problem. And typically, the output of a pre-final layer in this deep CNN before the softmax layer, we can take it as the representation of the image here, and then use it for any other task that we are interested in. And with the invent of these deep learning models, there are much more challenging tasks that are being explored, especially in the image and video processing domain. And one such challenging task is what is called an image caption. All along we have been talking about image classification, where given an image, we want to only give a label to that image. Now the image captioning is a much more challenging task, where I want to generate a sentence that describes the content of an image, right? So given an image like what is shown here, maybe a typical caption can be a group of people at an outdoor market, or given the bottom image here, the caption can be a woman holding a camera in crowd. So now I cannot use a simple CNN to solve this problem, because a simple CNN can give only a label to this image, right? But this cannot generate a sentence as the output of the model, right? So now we need a model which can take an image as input and then generate a sentence which describes the content of the image as the caption. Okay, so typical structure of a system which performs this image captioning is what is known as the encoder-decoder paradigm, where there is an encoder which takes the image as input, and typically it's a deep CNN like a VGGNet or SNet or any of these models. So the purpose of this deep CNN, which acts as the encoder, is to get some representation of the image as a feature vector, right? And that feature vector will go as input to what is called a decoder, which is capable of generating a sentence as the output of the model. And typically one uses a recurrent neural network, which can generate a sentence as the output, and that sentence will be the caption. So basically these two modules are put together to build a image caption system. Then we can collect a large number of images along with the captions given by the humans, and then train this whole system. And after the system is trained, if I give a new image, then the system will try to generate the caption for that. Okay. So basically we need a model here which generates the sentence as the output, which the recurrent neural networks are capable of. Again, there are many types of recurrent neural networks, and one of the most commonly used recurrent neural network nowadays, which is a deep learning model, is the long short-term memory based recurrent neural network. So typically this LSTM model is used as the decoder, and some kind of a deep CNN is used as the encoder in the encoder-decoder paradigm-based system for the image captioning, right? And this decoder generates a sentence like this. In this case, young person drawing face on the sheet. That's what the content of this image kind of suggests, right? So now we need this kind of recurrent neural network, which can generate a sequence of words as the output, okay, which the LSTM models have been shown to be very effective. And what you're going to see are some other tasks in other domains, like speech processing tasks, where we have to deal with the sequential type of data. Like if you're talking about speech recognition, what is shown here in this slide are the waveforms of 3 different utterances and the corresponding text for the waveforms of each of the utterances. Only thing is the text is given in English, but actually this utterance belongs to a different language. As you can quickly see, the first utterance here belongs to Hindi, second belongs to Tamil, and the last one belongs to Telugu, right? What are we trying to do here? Given the speech signal of an utterance, we are trying to generate a sentence that represents that utterance. So basically we are doing what is called a speech recognition, which involves converting the speech into the text. And as you can see here, the speech signal is a sequential pattern, right? And the output here is also a sequence, which is a sequence of, let's say, words. Okay. So here we need to perform conversion from one type of input sequence to another type of input sequence. That is typically the speech recognition task. There are many other types of tasks related to speech domain. And another task is what is called a speech-to-speech translation task, where given the speech in one language, can we generate the corresponding speech in the another target language, which is a much more complex task. But this requires a speech recognition system, which will take the source language speech and converts that into a sentence. And then we do a machine translation using the machine translation system, which generates the target language sentence. Then we use a text-to-speech synthesizer to generate the corresponding speech for the target language sentence, right? So in all these tasks like the speech recognition and speech-to-speech translation, there is what is called a sequence-to-sequence mapping task, okay? But there are a number of other tasks even in the text processing domain, which are normally referred to as the natural language processing domain, where we typically deal with machine translation tasks or the text summarization tasks, right, or question answering tasks, where typically the input is some sentence or a text, and the output is again some sentence or a text. And each sentence or text is considered as a sequence of words, which means that the input is a sequence and output is also a sequence, right? So what we need to perform in all these tasks is what is called a sequence to sequence mapping task. And this is a much more complex task than a sentence classification task, where given a sentence, we want to, let's say, I'm talking about a sentiment classification. I want to identify what is the sentiment associated with a given sentence. It's a more of a classification task that involves sequential data as input. Okay, but or similarly the named entity recognition. But the sequence to sequence mapping task is a much more complex task, where it takes a sequence as input and then generates another sequence as the output. And as you'll be seeing, the transformer models are mainly designed for this kind of a sequence to sequence mapping task. Like if we talk about the neural machine translation, where we are talking about translation of a sentence in the source language to a sentence in the target language. What are the sequences here? The input is a sequence of words and the output is a sequence of words. In the speech recognition system, which is basically a speech text conversion system, conversion of the speech signal of a sentence utterance to the corresponding text of a sentence, right, is the task. So the input is a sequence of feature vectors that are extracted from the speech signal of a sentence, and the output is the sequence of words in the text form that represents the sentence. So it's also a sequence to sequence mapping task. Or whatever we talked about as the image captioning task can be extended to a video captioning task, where I want to give a video as the input and then generate a sentence as the caption, which describes the content of that video, right? Again, the input here is a sequence of feature vectors extracted from the frames of a video. And what we need to generate is a sequence of words that represents the caption for the given video, right? So all these tasks involve mapping an input sequence to an output sequence. So now we can extend encoder decoder paradigm from this sequence to sequence mapping task. And here we give the input sequence to the system. Then there is an encoder, and now it generates the representation of this input sequence. And obviously I cannot use a CNN kind of a thing, because CNN is used to encode the image type of data. So what we need here is a kind of a recurrent neural network. So typically one can use any type of recurrent neural network to take this input sequence and then generate some kind of a representation of that sequence, typically in the form of a feature vector. And that feature vector goes as input to another recurrent neural network, which acts as a decoder and then generates the output sentence. Like in the case of the machine translation, the input sequence is the sentence in one source language, and the output sequence will be the corresponding sentence in the target language. Like if you talk about Hindi to Tamil, right? Then we are talking about a sentence in Hindi language being given as input here, and then this system generating the corresponding sentence in the Tamil, right? So this is the kind of paradigm that we are talking about for performing the sequence to sequence mapping task. And what we are going to see is how the transformer models are mainly designed for this kind of a task. And when we want to perform this sequence to sequence mapping task, right, there are a lot of issues in that. Okay, first of all, the lengths of the sequences will be different, and that's what is effectively handled by the recurrent neural networks, right? But we want to capture the relations among the elements of the sequence. What do you mean by the elements of the sequence here? If I'm talking about a sentence, which is a sequence of words, many words in a given sentence are related to one another. They are not completely independent words, right? So when you are performing the sequence to sequence mapping task, it's important to capture the relations among the words in each of the sentences, right? And that's what the models try to do. So in the sequence to sequence mapping using the encoder decoder paradigm, we want the encoder to generate a representation of the input sequence, and then that representation generated by the encoder is given as input to the decoder, and then the decoder generates the output sequence. But it's very important to capture the relationship among the elements of sequence, right? Typically, an element in the input sequence is related to a few other elements in the sequence, same sequence, right? And similarly, a word in the output sequence to be generated is also related to the few elements in the input sequence. That is, let's say if I'm talking again a translation task, if I want to generate a Tamil word, it's not generated only from the corresponding Hindi word. It is related to many other words in the Hindi language sentence, which we are giving it as the input, right? So it's important to capture that relationship and perform this mapping task. Okay. And LSTM models have been extensively used for the sequence-to-sequence mapping task. Typically, one uses a bidirectional LSTM-based encoder and a bidirectional LSTM-based decoder, mainly because this can capture the dependencies among the elements in the given sequence in both the directions, both in forward direction as well as the backward direction, right? And each of these bidirectional LSTMs captures the relations within one sentence. Okay, that is, the encoder captures the relations among the words in the input sentence, whereas the decoder tries to capture the dependencies among the words in the output sequence. But in order to capture the dependencies of the words in the target language sentence on the words in the source language sentence, right, we introduce what is called the attention mechanism, which basically tries to capture the relationship between a target language word with respect to the source language words, okay, in the context of the machine translation task, right? Similar kind of a thing exists in the other sequence-to-sequence mapping tasks, right? But as all of you might know by now, right, LSTM model is very complex, right? The number of parameters is large, especially if you're talking about bidirectional LSTM. The number of parameters to be estimated is large. And also when you use the training method, backpropagation through time, it's a computationally intensive method. And also there is not much of scope for parallels of the operations in the training of these models. Therefore, the amount of time required to train such a sequence-to-sequence mapping system is enormously large. Okay, and also there's not much of scope for parallelization of the operations. Even if you have the GPUs, right, it's not easy to perform the parallelization of operations and then make use of the GPUs, right, to reduce the training times. And what you are going to see is that how the transformer models can be used to perform this kind of a task where there is a lot of scope for parallelization of the operations, so that one can reduce the training time significantly compared to this LSTM-based models. And this paper in this conference in 2017, which has got a very interesting title, attention is all you need to perform any of these tasks. Okay, and as the name itself implies, right, what all we need to mainly use is the attention among the elements of the sequences, right? And what are these attentions that we are talking about? Basically, it's relations among the elements in the input sequence, which is now going to be referred to as what is called self-attention, right? And similarly, relations among the elements within the output sequence will be called as again the self-attention. And when you want to capture the relation between the elements in the input sequence and the elements in the output sequence, right, then it will be referred to as the cross-attention. So as we'll see later, we make use of both the self-attention as well as the cross-attention to perform this task of capturing relations of different types, and then make use of these relations in performing this sequence-to-sequence mapping task. Okay, you would have come across this kind of a diagram whenever you gone through the paper on transformers, right? This is a diagram taken from this paper, right? And you see several blocks here, right? And there's what is called an input embedding, output embedding. Then there is what is called a multi-head attention, and so on. What we are going to focus in the next few slides is try to understand what is this multi-head attention. And typically, this input embedding and output embedding depends on what is the type of data that we are dealing with. If it is a text data, then we typically use what is called embedding of words. There are many types of word embedding representations, like word-to-vec representation or glow representation. Or if you are talking about speech data, we are going to use a speech signal processing methods to extract certain features from the speech signal and then use that as the input sequence. Or if it's a video data, then from every frame we get some kind of a features extracted, and that will be the embedding that we are talking about, right? So this embedding depends on what kind of sequential type of data that we are dealing with, and accordingly make use of the embedding method to generate a representation and then use that as the input to these models. As you can see here, there are two modules. One is the encoder module and the decoder module, right? Again, the encoder module processes the input sequence and then gets some representation, and that representation goes as the input to the decoder module, and then this generates the target sentence or the output sequence. Okay, So what we'll be looking at next few slides is trying to understand what we mean by this attention, what is this called as the multi-attention. Then finally, we'll come back to this block diagram. Okay. First, we'll try to understand a term called the scaled dot product attention. And the terminology that we'll be using in defining the scaled dot product attention is mainly borrowed from the linear regression methods for the function approximation. What do we do in this function approximation? I have a function of d variables, let's say x1, x2, so on, xd, and the function is f, right? And if I put all these d variables into a vector x, right? Now this function f is of this vector x. So what is the function approximation task here? Given a set of n examples in the training data set where I have the xn, which is the nth example, and the corresponding desired output, which corresponds to the value of this function for that example xn. And if I collect n such examples, now I want to build a model which after training can predict the estimate of y equal to f of x, where x is some new example, and I want to estimate the corresponding value of f of x. We will not get exactly the same f of x, we will get only an estimate of that, that's the y hat. There are a number of methods to perform this function approximation task. What we do in the linear regression method is I try to estimate this y hat using x and xn and yn, right? Xn and yn are part of the training examples, and x is the example for which I want to estimate the f of x, right? And in the context of linear regression method, we refer to this x as the query because that is the example for which I want to approximate the function, and the corresponding training examples xn are referred to as the key vectors, and the desired output values for each of these examples are what are called as the values. So y can be estimated as the summation of some function g of x comma xn, and then that value of this function is multiplied by the value yn. Okay, this g is normally referred to as the basis function. Typically we use a Gaussian basis function which looks at the Euclidean distance between the x and xn and gives some kind of measure of similarity, and that measure of similarity is used as some kind of a weight that's applied on the yn. Now we can see that this y hat is obtained as a linear combination of this yn, where the weights are determined by the value of this basis function, which in turn is related to the similarity between the query and key, right? As you know, the Euclidean distance between two vectors can be used as a measure of dissimilarity, or one can use the dot product between the two vectors as a measure of similarity, right? As we'll be saying quickly, we will make use of this dot product based similarity in order to perform this kind of a function approximation, but we will not be talking about function approximation task. But what I want you to note here is that the query corresponds to this x here, and the key corresponds to one of the training examples, and yn corresponds to the desired output. Okay, and we try to compare the query with the key and estimate some kind of a similarity measure, and use that similarity measure as some kind of a weight also applied on the value, using which we try to generate the desired output here. Okay, and we'll be using this kind of terminology in the attention-based models, but we'll be dealing with the vectors, right? And typically we'll deal with the d-dimensional vectors, right? And the sequence consists of several such vectors. The total number of vectors is capital T. Okay, so we'll have what are called the query vectors and key vectors, which are denoted by k, and value vectors v. Now we define what is called the scaled dot product between a query vector, that's qt, and a key vector km. We'll be seeing what are these query vectors and key vectors with a specific task a little later. Okay, so these two are vectors. So I compute the dot product between the two vectors to get some kind of measure of similarity, and then I want this measure of similarity to be independent of the dimensionality of the data that we are dealing with. So we divide it by d, so that gives us what is called the scaled dot product. And this alpha tm is a scaled dot product between the query vector qt and the key vector k. Then we define what is called an attention score, where we map this scaled dot product values into values which are in the range 0 to 1, you can kind of indicate them as the probabilities, but the probability is not an appropriate entity here. I would say it's a measure of similarity on the scale of 0 to 1. As all of you know, the output of the softmax function is in the range 0 to 1, right? So on the scale of 0 to 1, how close is this query vector with respect to the key vector is what we are trying to estimate. And of course, with respect to all the key vectors, if you add up this attention score, it will be 1. Okay. So basically, we are getting some values of this attention score, which are in the range 0 to 1. And then we use these attention scores to come up with a what is called a context vector that can be associated with this query vector. Please remember that the query vector is fixed. And when I change the key vector, I'll get the different scale dot product values. And therefore, I'll get these different attention scores. And associated with every key vector, there is a value vector. So now what we do is we combine these value vectors by multiplying each of these value vectors by the corresponding attention score, and then find a linear combination of these value vectors to generate this context vector, which is associated with this particular query vector, right? So this is what we do when we perform this scaled dot product attention, where given a query vector, we generate this new vector called the CT vector, which is the context vector. What are we using in this? We are using this attention scores, which are obtained by comparing the query vector with all the key vectors. And we also use all the value vectors. And because we are using all the query vectors, all the key vectors and the value vectors, right, we can express this context vector as a function of the corresponding query vector and this K matrix and the V matrix, where K is the key vector matrix and V is the value vector matrix, right, where the columns of these matrices are nothing but the corresponding key vectors and the value vectors. So basically, this scale dot product attention involves comparing the query vector, given query vector, with all the key vectors, and then generating these attention scores and using them to generate the context vector by a linear combination of the value vectors associated with the key vectors. So basically, it tells us how this QT is related to the different key vectors, and then we use that relation to generate this context vector as a combination of the value vectors. So basically, we are getting some kind of a new representation for each of these Q vectors, and that's what we want to use in the processing. But please remember that it's not any simple transformation. Here we make use of these attention scores, right? So if the attention scores kind of capture the similarity relationship between the different vectors here, right, then we are trying to capture that relations, right, in generating these context vectors. Okay. Now we introduce a term called self-attention, where we typically want to capture the relations among the elements of a particular sequence, right? Let's say if I'm talking about the sequence X here, where the elements of the sequence are the d-dimensional feature vectors, X1, X2, so on, X capital T. Again, if I'm talking about the machine translation task, this X1, X2, Xt can be the word-to-vector representations of the words in a sentence. Okay. Now we generate these query vectors, key vectors, and the value vectors. All these vectors are generated by doing some processing on these elements of the sequence in the X. Okay. But only thing is we do some kind of a transformation and then generate these query vector, key vector, and the value vector. As you can see here, this query vector Qt tilde is obtained by performing the transformation on the Xt, which is an element of this sequence, where this transformation is represented by a parameter matrix or the weight matrix WQ. And WQ is associated with the generation of the Q vectors. And similarly, there is a parameter matrix WK to generate the key vectors, and another WV matrix, right, to generate the value vectors. But all this query vector, key vector, and the value vectors are generated from the Xt itself, and we'll be doing the scale dot product attention on this query, key, and the value vectors, which are generated from the elements of the sequence. That's why it's called the self-attention, because we are trying to capture the relations among the elements of a particular sequence. Now, if I take a particular query vector here, and then perform this scale dot product addition to generate the corresponding context vector, right? We are trying to capture the relation between xt with respect to all the other elements of the sequence and then generate this context vector. Okay, that's why it's called the self attention. That's what is kind of illustrated in this diagram also here. As you can see here, xt goes as input to all these blocks with the different parametric matrices, and then we generate the query vector, key vector, and the value vector. Then we apply the scale dot product attention in order to generate this context vector C. Okay, and typically, as we see for certain reasons, the W matrices here are of size L cross D. D is the dimensionality of these feature vectors in the input sequence, and typically L is less than D, right? And these L dimensional representations are what are being processed here, right? And then this CT vector is also going to be of L dimension, right? And then we put all these CT vectors that are generated for all the elements in the sequence in the matrix to define what is called a context vector matrix, right? So this process of generating this context vector matrix from the sequence X using one set of these transformation matrices WQ, WK, and WV is what is known as a single head attention. As you might know, when we perform a vector by a matrix, right, what you're doing is nothing but a linear transformation, right? Actually, the transformer term represents capturing the relationship by performing various types of transformation. So here is one type of transformation that we are doing. It's a simple linear transformation, right? And that's why these weight matrices are also called as the transformation matrices. Here, given a sequence, we are using one set of transformation matrices to generate one context vector, which tries to capture some kind of a relations between the transformed entities, which are in the form of these Q vectors, query vector, T vector, and the value vector. What happens if I change these transformation matrices? I get new representations for the query vector, T vector, and the value vector, right? And that will help us to generate new context vectors, therefore a new context vector matrices, right? So what we do in the self-attention and the multi-head attention is we use multiple sets of these transformation matrices to generate multiple context vectors. And now we represent each of these set of transformation matrices being associated with what is called a head. So now you can see that for the ith head, I have these transformation matrices WIQ, WIK, and WIV. And when you use these transformation matrices of a particular head to generate the query vectors, now you can see that it's QIT tilde, KIT tilde, and VIT tilde. Then when we perform the scale dot product attention, we get this C tilde IT. And this we can do using certain number of heads. Again, that's a hyperparameter. And if I use the H as the number of heads, and typically the dimensionality of all these query key vectors and the value vectors will be related to the original dimensionality of the feature vectors, the sequence D and this H. So this L is equal to D by H. Again, we'll be seeing the reason for that trick. So depending on the number of heads that you use, right, the L will be accordingly related to D and H. So let's say typically if I use a 2048 dimensional vector to represent a word, and if I use 4 heads, then we are talking about 2048 by 512 dimensional representation of this query vectors. Okay. So now for every element in the sequence, we get the corresponding context vector using a particular ith head, right? And if I put all these context vectors for a particular element in the sequence, which is generated by using different heads, like you can see here, I'm talking about this C tilde 1T, C tilde 2T, C tilde HT, right? So I concatenate all of them to generate a context vector that represents the original feature vector that I have, that is the XT. Now, because each of these context vectors is of dimension D by H, when I put H such vectors together, I get C tilde T, which is also of dimension D. That is the reason why we are talking about this L is being smaller than D and L being related to D and H in this manner, so that the C tilde T can be having the same dimension as the original XT. So basically we are getting a new representation for XT, and like this we generate a representation for every element in the sequence to generate a new representation for the original sequence. And that representation is used again to generate as the output of this multi-head attention, which is called as the Z, where this Z1 tilde is obtained by performing a transformation on this C tilde T with the transformation matrix WO, right? So basically what we are doing is, after we generate this C tilde T, we multiply that with the WO vector to get the Z tilde T. Now we put this Z tilde T vectors together to form this matrix Z, which will be actually the output of the multi-head attention, or which is the sequence, right, as the output of the multi-head attention. So what is important to note here is that the input to this multi-head attention is a sequence, and output of the multi-head attention is another sequence, but the representations are different. The input representation is what we have generated by extracting certain features from the original data, and by going through several transformations, we generate a new representation, and that new representation is the output of this multi-head attention. But here we are talking about this multi-head attention, which is obtained by performing the self-attention. As we'll be seeing later, this self-attention multi-head attention forms a sub-layer in the encoder layer of a transformer model. Okay, again, whatever we discussed so far is what I'm showing you here pictorially. What is shown here is the operations done within using one head. Like you can see here, for head 1, I take XT, then multiply that with the corresponding transformation matrices to generate the corresponding Q vector, K vector, and the V vector. And then we perform this scale dot attention. Then we generate this context vector. And once we obtain the context vectors using the different heads, in this case 4, I put all of them together to generate the total context vector that represents this XT. And then we perform the another transformation to obtain ZT. And these ZTs are put together for all the elements of the sequence to generate the output sequence. Okay. Yeah. Now what we have done is going through one type of transformation using multiple heads and then generate a new sequence. And as we'll see quickly, we also perform one more kind of a transformation using what is known as the position-wise feed-forward neural network. So earlier we got one representation for every element in the sequence. So for X1 we got Z1, for X2 we got Z2, and so on, right? So we pass this Z1 through a multi-layer feed-forward neural network, mainly because whatever we've done in the multi-head attention is basically linear operations. We have not performed any non-linear operations anywhere in the multi-head attention, right, except for its softmax operation, right? But we want the model to have the non-linearity, because only the non-linearity can be helpful to solve fairly complex tasks, right? So now we bring in that non-linearity in the form of a standard multi-layer feed-forward neural network, which takes this ZT vector as the input and then goes through several nonlinear layers. Typically the hidden layer and the output layer are nonlinear layers, right? And then we generate a new representation called the X tilde T. So please remember this Z tilde is generated from X by using the multi-head attention, and then we pass this Z tilde to through this multi-layer feed-forward neural network to generate the new representation X tilde, which is now related to the original representation in a nonlinear way. Now this is done in parallel for each of these elements in the sequence, right? So now we can see that there is scope for parallelization of all these operations. There is also scope for parallelization of all these operations in the multi-head attention. So that's where the advantage of this model comes to the picture compared to the LSTM model, because there is a lot of scope for parallelizing the operations here. So whatever we have done now here is what is done in one layer of encoder in the transformer model. So the encoder layer typically takes the original sequence as the input. First, it performs the self-attention multi-head attention to generate the sequence Z, and then it is passed through this position-wise feed-forward neural network to generate a new representation of this X, which we call as the X tilde. But please remember that the length of this sequence is exactly the same as this, and the dimensionality of this is also same as the dimensionality of X. Okay. But this forms only one layer in the encoder module because we are going through only one set of transformations, both linear transformations in the MHA and nonlinear transformations in the position-wise feed-forward neural network. And that one level of transformations will not be adequate. So typically, we go through multiple such transformations to build the encoder module where there will be several layers of this encoder. So whatever is shown in the previous is one layer of encoder. So now the input sequence goes through the first encoder layer to generate X1 tilde sequence. That's given as input to the second hidden layer to generate the X2 tilde and so on. If there are L layers, right, then finally we generate the sequence XL tilde, which is going to be actually the output of the encoder module. Okay, but please remember that we have generated this XL tilde output of the encoder module from the input sequence by going through several layers, where in each layer we perform one set of multiple linear transformations and one set of nonlinear transformations. And when we are doing these transformations, we are capturing the relations among the elements in the sequence and then generating this output of the encoder module. So basically, we are trying to get a new representation from this sequence X, right, which captures the relations among the elements in the sequence and then generates the new representation. And this output of the encoder module goes as input to the decoder module. And the decoder also has a similar structure. But what is the decoder's function? It has to take the representation of the input sequence as input and then generate an output sequence. Let's say in the case of translation task, the encoder generates a representation of the source language sentence, and the decoder should generate the target language sentence. Okay. But we need to capture the relationship among the words in the target language. So first, what we do in the decoder module is perform this self-attention on the elements of the target language sentence. During the training process, we know this. We have this sequence of words in the target language sentence. So we can perform this conventional self-attention, multi-head attention. Then we get a representation of that. And now we use this representation of the target language sentence as the query vectors. That's what is indicated here. As you can see here, the sequence of vectors that's generated from the target language sentence is used as the query vectors, and the output of the encoder module is used as the key vectors and the value vectors. So basically, we are trying to capture the relation between each of the words in the target language sentence with respect to the words in the source language sentence. And because we are talking about capturing the relationship between two different sequences, this is referred to as the cross attention, multi-head attention. And this in turn generates a sequence. Again, we perform the nonlinear transformations in the position-wise feed-forward neural network and then generate the output of this layer of the decoder. And this represents a new form of the target language sentence that we want to generate. Okay, but this takes into consideration the relationship of the elements of the target language sentence with respect to the elements of the source language sentence, and then gets a new representation. Again, one level of transformations will not be adequate. So typically we go through multiple layers where, again, I have the decoder layer 1, decoder layer 2, and so on, decoder layer L. Sorry, there is a mistake here. It should be decoder layer L, right? And finally, the output of this final layer will be the representation of the target language sentence, and that we give it as input to as one more level of linear transformation, and then finally softmax layer, so that we can generate the probabilities for the different words in the target language, so that we know what is the word that is generated at a particular point of time from the source language sentence, which goes through the encoder and the target language sentence during the training process. And then the output of this decoder module is to generate the probabilities for the different words in the language, which can come as the next word in the sequence in the target language during the testing phase. So in the training phase, the desired output sequence is given as input to the decoder module, but during test phase, we don't have that with us. So we start with the initial word, and only give that partial sequence as the input to the decoder, and then use that to generate the output probabilities for the next word that can come. Then we use that next word along with the first word as the input to this decoder module. So what we get as input to this decoder module during testing phase is the sequence of words that are generated up to a particular time t, and again the relationship among the words is captured in the decoder multi-head attention module, right? And then that's used along with the representation of the source language sentence in order to predict what is the next word that can come in the sentence that's going to be generated by the decoder module. Okay, so as you can see here, all these operations in the encoder and decoder modules in the transform model are based on the transformations, which are linear transformations or the non-linear transformations, right? And there's a lot of scope for parallelizing the operations within the multi-head attention and within the position-wise feed-forward neural network. And that's what will enable us to train these models much faster than the LSTM models. So whatever we have discussed so far is what forms as the components of this block diagram that I have showed you in the beginning. So this multi-head attention in the encoder module does the self-attention. This masked multi-head attention does the self-attention in the decoder. This is masked because during the testing phase, we have only part of the sequence available as the input. And the second multi-head attention performs the cross attention between the representation of source language coming from the encoder and the representation that we derived from the self-attention in the decoder. And then we pass it through the several layers of the decoder and finally generate the probabilities for the next word that can come in the sequence in the generation of the target language sentence, right? So this is what indicates the operation of the transformer. Of course, I have skipped some of the details like what are called these add and NOR blocks, which are based on what is known as the residual network principles, where we take the output of this block here and then give it as the input, and then we add the output of this feed forward to this and then perform some kind of a normalization, right? And the basis for that is whatever is done in the residual network. Okay, but the most important thing here is to understand the role of this multi-head attention to generate the representations of sequences and then use them to perform this sequence to sequence mapping task. There is also what is called the positional encoding. Depending on the position of a word in the given sequence, right, we need to inform or we need to encode that position information into the sequence that we give as input to the encoder and the decoder. There are different ways of encoding the position information. One can use any of them and then generate the representation that goes as input to the encoder and the decoder, all right? And then we perform all these operations to perform the sequence to sequence mapping task. As I said, this model is mainly suitable for performing variety of sequence to sequence mapping tasks like machine translation or speech to text conversion or video captioning. Interestingly, it's also being used for image classification task, where we divide the image into parts, which are called the patches. Then we get one representation for each of the patches by passing it through some kind of a feature extraction module. Then we get a sequence of feature vectors that represent the sequence of patches here. That goes as input to the encoder module in the transformer. And we get a new representation for this sequence. And that information is used to perform the classification task. And this is what is called as the vision transformer, which can be used for the image classification task. It has been shown that this vision transformer gives a comparable performance with the deep CNN model, but the training of this model is faster than the conventional deep CNN. And there is also the application of this transformer model for a task like the dense video captioning, which involves, given a video, we identify the different events associated in the video. Then for each event, we try to come up with a caption and then put all these captions together to generate the caption for the whole video. This is what is referred to as the dense video captioning, as illustrated here. For one part of the video, we come up with one sentence. For another part of the video, we come up with another sentence. And once all these sentences are generated for the different parts of the video, we put all of them together to generate the caption for the given video. This is what is referred to as the dense video captioning. There is one paper which talks about performing this dense video captioning using a transformer. As you can see here, the different frames of video are passed through the deep CNN model to generate a representation. So we get a sequence of feature vectors. We pass it through the encoder module here, and we also pass the output of this encoder module to what is known as the event proposal generator, which indicates what are the different events associated with the different parts of the video. And we combine that information, and that information goes as input to the decoder module, and that decoder module generates the caption for the complete video. Okay, and the glow embedding is one of the representations of the word embedding, which is used here for the caption during the testing as well as for the training process. Okay, so this is an interesting application where we combine the CNN models and transformer to perform captioning task, but essentially it's a sequence to sequence mapping task. So what I wanted to convey to you is that the transformer models are mainly designed for sequence to sequence mapping tasks, and they can be used for any domain as long as the input is one sequence and the output is also another sequence. And in comparison to the LSTM models and the CNN models, the main advantage of the transformer models is the scope for the parallelization of the operations, leading to significant reduction in the training times. Of course, the number of parameters is much larger, though the weight matrices across the layers are shared. And as you have seen, the weight matrices associated with the multi-layer feed-forward neural networks in the position-wise feed-forward neural network are also shared. Still, the number of parameters to be estimated is large. Therefore, one requires large amount of training data to train these models. Okay, there are a number of techniques that are being explored, like pre-training methods, to deal with the requirements of large amount of labeled data to train these transformer models. So these are some of the current works that are going on related to this transformer models. So with that, I would like to stop here and thank you for your attention, and take any questions that you may have.
Thank you very much, sir, for the nice and informative lecture. Actually, really, it was interesting, and I hope all our participants will be would have been able to follow, because you covered all the basics and the essentials for understanding these difficult concepts. So we'll go for the questions. Participants, if you have any questions, either you can drop it in the chat box or you can raise your hand and ask your questions. It's a very good opportunity to interact with expert like sir. So kindly utilize this opportunity, please.
Okay, there are a few comments or questions. I'm not sure.
I think that's for the previous session, sir. I think.
Oh, okay. No, but something are there about the VAT, and I don't know.
Yeah, sure.
Okay. VAT can be used for unsupervised classification. No, I'm not saying that. Right? VAT is still used to perform the supervised classification only, but only thing is you bring in the transformer model, right, to perform the classification task. So it's still a supervised. Yeah, what steps to follow for the image classification task? Divide the image into patches, generate a representation for each of the patches, then you form the sequence, give that sequence as input to the encoder, and then output of the encoder is given as input to one more multi-layer model, and that performs the classification task. As given in the diagram, please go through that diagram and also the paper, right? So basically, instead of giving the image, complete image as input, like what we do to the CNN, here we divide the image into patches and then generate a representation for each of the patches, and use those representations to form the sequence and give that sequence as the input to the encoder module of the transformer. There is a lot of work going on in the applications of transformers in the NLP. Actually, transformers, I would say that mainly have come mainly because there is so much of scope for their use in the NLP, right? One of the applications I said is the machine translation, and one can use it for the text summarization or question answering. Because what is the question answering? You have some text and a question. So both are kind of sequences, right? And one has to take these two sequences as input and then generate the answer for that question from the text. So the output is also a sequence. So there are a number of interesting applications of the transformer for the text question answer task or the text summarization. What is the text summarization task? The input is a text, which is a collection of sentences, and output is summary of that text, which is also a sequence of words, right? So you can use the transformer model to perform this text summarization. So any task that involves sequence to sequence mapping can be typically carried out by the transformer model. Yeah, if you're asking for the research direction, there is a lot of work that's going on how to build more efficient transformer models. There is what is called the DELIGHT model, which stands for the deep and light transformer, where the focus is on how to reduce the complexity of this transformer model without reducing the performance of the model, without affecting the performance of the model. Okay. Yeah. Good. Any other questions?
Okay, I hope, yeah, we don't have any more questions, sir. Actually, I think you may not mind if they will email you with, if they have some queries with regard to, again, maybe when they will go through the presentation and your recorded videos.
Sure.
So kindly.
There is one final question here.
Yes.
Image sequences should not be time dependent. If you are talking about video, no, typically the order in which the images are present is important. Okay, so let's say if you're talking about a video, which you can consider as a sequence of images, right? So the position of the images is important. That's why the positional encoding is done, right? Yeah, again, I don't know what is this question, because we already talked about the relevance of these encoder decoder models for text-to-text generation, right? That's what we do in the typical translation task. Yeah. Okay. Fine. Okay. If there are any further questions, you can send an email to me, right?
Sure. Thank you very much, sir, for the